So we will launch into things. We've got a packed house both here in the classroom and on Zoom. I see several people online as well. So very excited to kick things off this morning. So it is a pleasure to be welcoming and introducing Professor Jayant Baliga for today's colloquium. If you noticed carefully in the flyer, this is more than just a regular colloquium. We're actually referring to this as a distinguished colloquium in recognition of Professor Baliga's great contributions to the university and to the research field. So he will be telling us today about his, I think, quest for the ideal power switch. If you don't already know, Professor Baliga has been really a true pioneer in the area of semiconductor devices for power devices and power electronics. And so I think it'll be very interesting to hear your perspective on how things have evolved over the years. So just a few more words about Professor Baliga's background. He spent 15 years at the GE R&D Center, leading the power device effort there, and was bestowed the highest rank of a Coolidge Fellow. He invented and commercialized the insulated gate bipolar transistor, or IGBT, at GE. And if you don't know, the IGBT is truly one of the most important devices that's out there supporting power systems around the world. Since joining NCSU in 1988, he has been recognized with the Alexander Quarles Holiday Medal and the O. Max Gardner Award. He's launched 4 startup companies with successful products, the superlinear RF MOSFET, the TMBS rectifier, the SSC FET, and the GD MOSFET, which are in production. He has authored 27 books and over 700 publications, and he was honored the National Medal of Technology and Innovation in 2011 by President Obama, the IEEE Medal of Honor in 2014, and the Global Energy Prize in 2015. He holds 123 U.S. patents and was included into the National Inventors Hall of Fame as the sole inventor of the IGBT in 2016. So really a big milestone there in contribution. Before I hand the microphone over, I just wanted to remind everyone that on Zoom especially, that we are using sort of a webinar format for this, which means that if you're participating in Zoom, there's no audio, but you can submit questions via the chat and Q&A function, and we'll look for those at the end of the talk, I think. So if you have a question about a particular slide, make sure in your question that you refer to that slide so we can look that up afterwards and answer the question appropriately. So with that, I will hand over the microphone to Professor Baliga.
Thank you.
Yes.
Well, good morning, everyone. It's great to see so many bright faces here this morning. And of course, lots of people joining us online as well. So the organizers asked me to speak on this 35th anniversary for me here at NC State. So I said, hey, I better review what is it that I've accomplished in my 50 years doing work in the semiconductor field. And I found a common thread, which is my quest to find the ideal power switch. So I thought that would be a nice way to talk about my experience. So that's what I'm going to do today. But when let's see if this works. It's not advancing.
Might want to click to put the mouse on the screen.
Here we go. So I decided I should make my talk interesting. So this was the first attempt. I said, let me call it India J's Quest for the Holy Grail, ideal power switch for power electronics. But I was worried that the organizers may not take kindly to that title, so I changed it. But this slide shows me wearing my Indiana Jones hat and going all over the world looking for the ideal switch. I'm sorry to say I couldn't find it. Sorry, folks. However, that's because the ideal really doesn't exist, right? The ideal is perfect. You cannot have something that's perfect. So I have found lots of other switches that are close to ideal, and that's what I'm going to talk about in this presentation. All right, let's see. So before I tell you about the ideal switch, I'll tell you that this has been a journey of many discoveries, and I'd like to think about them as gems that I've discovered and found. So let me share some of those with you. First is in the area of process technology. You may not know, but I accomplished the first planar junctions in gallium arsenide. That was pretty cool all the way back in '72. I pioneered the growth of MOCVD layers of indium arsenide, gallium indium arsenide, first time. Showed the growth of zinc, tin, indium oxides, all of this became highly commercialized. MOCVD is now the technique used to make many, many layers. And then I did some other work, which is interesting, like the only person to grow silicon out of the liquid phase, etc. But turning to the power device area, I also did a lot of work on power rectifiers, which I will not talk about in this lecture because I'll focus on switches. But these are very important because you cannot do power electronics with just a switch. You need a diode. So one of them is the junction barrier Schottky rectifier, which I proposed back in '84 and showed that it works well in silicon. But today it's actually become the necessary technology to build all silicon carbide Schottky diodes by all the manufacturers. And that has already reached a market over $200 million. And also proposed the merged PIN Schottky rectifier, which some of these manufacturers mentioned. And then the TMBS rectifier, which stands for Trench MOS Barrier Schottky rectifier. This actually received a B.F. Goodrich Award at the Inventors Hall of Fame in the 90s, but it got commercialized later, and I'll mention that in my presentation. And then I worked on a bunch of devices called MOS-gated thyristors. These were quite successful. They worked quite well, but industry has not picked these up, so I won't talk much about those. Moving on, I did work on smart power ICs. This was first done at GE, where we were commercializing the IGBT, but we needed a smart power IC as drivers and for other applications. And I gave a talk at the IEDM, and after that, IEEE thought that was enough to give me the Liebman Award. I was quite surprised to get that. But we did pioneering work here at NC State on dielectrically isolated devices for the first time as well. And then I did a new type of device. It's called a superlinear device. It's got some very unique physics that I discovered. I was quite surprised that no one had discovered this physics after 50 years of work by thousands of people. And I said, let me try to get some patents, and they were all issued to me. So it's always interesting to find a whole new mode in which a transistor works. It doesn't happen very often. So I commercialized this device through a company, which I'll mention later. And then, of course, we are here because I said I'll talk about the ideal switch. So these are my attempts to create the ideal switch. Among these, I will talk about the silicon insulated gate bipolar transistor. I'll refer to this as IS1 on the slides, the first ideal switch. Then I'll talk about the split gate silicon GD MOSFET. This is based on some unique new charge coupling physics that I proposed. And this has become a very big product as well. And then I'll talk about silicon carbide-based devices. This is the third device, IS3. And this is based on some analysis I did way back on wide bandgap devices that I'll talk about. And finally, I'll talk about my most recent innovation done here at NC State. That's the BiDFET in 2020. And people in power electronics seem to be very excited about this. So as already mentioned, I have a lot of publications. These document all of this technology. You can read it. So I'm not going to get into all the technical stuff in this chart, in this presentation. I have also 123 patents that describe some of this. The number of books just went up. The book was published this month in addition. So I have now 28 books. And these are some of the books that I thought might be interesting to display. These are recent books. So you can find a lot of this material in the books. Each one is quite a volume. Some of them are quite heavy, actually, to carry around. So you can have fun reading all this material. Okay, so before I talk about the power semiconductor devices, let's look at what is an ideal power switch and why do we need it. So for a layman, non-electrical engineer, I like to say it's somewhat like a switch on the wall. Where's the switch on the wall? Way back there. Okay, so I've shown a mechanical switch here, and you can turn it on, and that will provide power from the AC source to a light bulb, and you can make it work. And of course, you don't want to do this very fast, but you could at most run it maybe once per second. So it's not very fast. But in power electronics, we need switches that can control the power flow very precisely. And if you can do that, you can do digital power control. That is done by pulse width modulation. And we have today electronic switches like the IGBT that can do this very efficiently, even on 100,000 times per second. So that's the basic thesis for why we need an electronic switch. Let's look at what it is that we need in this switch. Something happened to my slide, but what we need is a highly efficient manner in which we can do this with low power dissipation. So that requires a switch with low on voltage, so it doesn't dissipate power when it's carrying current through it, when the switch is closed. And then it needs to be working at high switching speed to do this pulse width modulation. We need switches that operate at high current density because we can then make the chip size very small. That's essential if you want low cost. Without low cost, nobody will buy your device. And then we need switches that are rugged so that you have reliable operation and people are happy with it in terms of applications. So that's been the quest, not since I started, but well before that. Before I started working on this around 1974 at GE, well before that, people were exploring how to get an ideal power switch. So what does that look like? A basic behavior is shown here in terms of the output characteristics. This is the current flowing through the device, the voltage across it. So we want it to work in the on state with 0 voltage drop, then it becomes ideal. We want it in the off state with 0 current. And then you want to be able to regulate the current flow through these characteristics. And you preferably want to do that with a voltage control, not current control, because we find we can integrate the drive circuit if you have a voltage control device. So that was one of the important things we had to do in the 80s. So if you have a voltage control device, the whole power electronics shrinks tremendously. So if this is an ideal device, it'll switch perfectly like this, where the current will change instantaneously, these 2 points, and the voltage will also change instantaneously. And the voltage drop will be 0 in the on state, current will be 0 in the off state with a high voltage, and these transitions will be instantaneous, so we get no power losses in the device, and therefore the power electronics has very good efficiency. So the device that was created before I started working in this field was the bipolar transistor. This is a direct offshoot of the invention of the junction transistor at Bell Labs, but they did not build power devices. They were interested in small devices for the telephone system. But other companies like GE and Westinghouse started looking at how to make a power device out of it. So here's the output characteristics for a bipolar transistor. And you can see that it has a very large so-called quasi-saturation region. So when it's in its on state, the voltage drop becomes large, and that is not good in terms of power losses. It is also a current control device. And unfortunately, when they built these devices, they could not get the gain to be much more than a 10 in the on state, and when switching as low as 1 or 2. So it was terrible in terms of the drive circuit as well. And furthermore, it had a long storage time during switching, which slowed down its switching frequency. So some other people said, hey, we are building MOSFETs for integrated circuits. Why not scale those up and use them for power? So that has been successful at lower voltages, but when we want devices to handle high power levels, like the air conditioners in your house or in a building or in electric vehicles, you have to have much higher voltages in these devices. And then the silicon power transistor MOSFET ends up with a very high on resistance, making it impractical. So the situation was depicted in this chart. So I put below here, what is it that we are seeking for our ideal device? So first we had the bipolar transistor developed in the 1950s. This is the cross-section of the device where it has an emitter at the top and a base terminal. So you provide base drive current to the transistor and get current flow through the emitter. And that then flows down into the collector, which is placed at the bottom of the chip. The reason for doing this is so that we can introduce a drift layer that supports high voltages. So now this becomes a power transistor. But all of these were designed with narrow P-base regions to try to get as high a current gain as possible. And then we relied on electron transport because electrons have better mobility than holes. by a factor of 3. So everybody who was making bipolar transistors focused on this kind of structure. So these companies were all on the East Coast, like GE and Westinghouse, but another group of companies on the West Coast started developing the MOSFET. So these are companies like Siliconics and International Rectifier. So this device is quite different. It has now an MOS structure at the top, and the current flow in this device is induced by applying a gate bias. When you do that, you get electron transport across a channel, and then these electrons flow into the drift region. So we also have a vertical structure here to be able to support high voltage in this portion of the device. So this device is fundamentally different in architecture, as you can see here. And as a consequence, we ended up with something that reminded me of what Rudyard Kipling said in one of his books. He said, "East is east and west is west. Never the twain shall meet." Now, he was talking about the British Raj in India. So he's talking about how the British and the Indians will never get meeting of the minds. Well, that was still true for this technology. There was a group of companies on the East Coast, another group of companies on the West Coast, and they felt they had very different technologies to build the device. This one, they optimized bulk transport. Here, they optimized surface transport, and these were considered to be incompatible. Well, in 1980, I decided to break that rule and propose the IGBT. So this is the basic concept of the IGBT. It has an MOS gate to create a channel, and then it has a P+ collector to inject holes. So when you do this, you end up with both electron and hole transport simultaneously. So this is now a MOS bipolar device, a new type of entity. So now we have to be able to control things at the surface and in the bulk simultaneously. So I thought that was a very new, innovative idea, but my colleagues all were greatly skeptical. You should have seen all the naysayers when I proposed it. Well, they were right. They had a lot of concerns. They said, what you have done is also built a thyristor. You have 4 layers, N, P, NP, and if you take my class, I'll tell you all about thyristors. And those devices latch up. And they said, this is going to latch up and destroy the device. You will never get gate-controlled behavior. You're wasting time. So I had to find a way to solve that problem. Then they said, oh, well, even if you solve that problem, your idea is very stupid because we all know that the best transistors have narrow base and electron transport. You're proposing a wide base PNP transistor. You're crazy. Not going to carry any current. It's just terrible. So those were 2 big roadblocks. But then they threw a third one at me saying, all process technology to control bipolar devices, we have to control lifetime in these devices. If you apply them to MOS devices, we know, we've already tried, the gate gets all screwed up. So there's no way to control the lifetime. So this device will only switch slowly, which has very limited applications. So why are we bothering to build this device? So I had to solve that problem. So unless I had solved those 3 problems, we would not have IGBTs today. So I'm given credit for creating the IGBT, not because I just invented this structure, but because I solved these 3 critical problems without which we would not have these devices. But then I did a 4th thing. I took this device from concept to a product in less than 1 year. Those of you at the university may not appreciate this, but if you're in industry, that, let's take GE, standard practice was to create a new innovation, work at the GE labs for maybe 2 or 3 years to find out how it works, find out all the flaws, figure out how to make it work, get a process going. And then you go to the production people and say, we have a new widget here. We want to build this. And say, what do you need? Oh, you need this new process. I need then to spend millions of dollars setting up a new process line. It's going to take me 2, 3, 4 years. So the whole thing takes at least 5 years. That was the standard practice. I said, no, I don't want to do all that. I want to go directly with my innovation. I've not made it, but I want to build it in the power MOSFET line because the upper structure is very similar. And I can modify this slightly and get a product done very fast. Well, if you go from a research lab to a production facility and say, can you do this new widget I want to build. They say, goodbye, don't even walk in the door. We're building product, we're making money. We don't have time for you to do your little research project. So something very important happened, which I cover in an article in a book that IEEE just released on the 75th anniversary of the transistor. So you can read that story over there. But a bunch of circumstances happened, and I not only had to pitch it to the upper management, but it went all the way to the chairman of the company, Jack Welch. Now, that doesn't happen very often because the chairman is worried about his, at that time, about a $10 billion business. He doesn't have time for a new small innovation in some research lab, right? But he was told that this is going to impact products across his company and have billions of dollars of impact. So you better pay attention. And so he said he wants to hear about it from me. And that is frightening, to be frank, to pitch something to the chairman of the company. And he had the reputation as Neutron Jack, and even the management was all terrified of it. So it was not a great prospect. But I said, this is my only chance. I have half an hour to convince Jack Welch that this is a good idea. I've not made the thing, so I'm taking a big risk here, but I'll do it. So I did it, and he liked it. Otherwise we wouldn't be here, I guess, talking about it. And he said, okay, this is so good that I want you to support Baliga, but we want to embargo all talk about this device because I want to milk this for all our applications at GE and make all our product divisions much more competitive than everybody else. So that was okay. So I said, now at least I have his blessing. And if I go to the product division and say, I want to make this device, and they say, no, I said, but you want to talk to Jack Welch? No, I don't want to talk to Jack. I'll do it for you. Sure, of course I'll do it. So I walked in and I told them, I will give you the starting material. I will design the chip and I'll give you the process. That's a slight tweak of your production process and you can run the wafers. So imagine at that point, I had the spotlight of the whole company on me. And if I had tripped anywhere, it would have been a total disaster. So fortunately, I did a flawless chip design and process. The very first wafers came out with functional IGBTs. And then I took my unique lifetime control process and tailored them for various applications. And now we had a product coming out in large volumes with different behavior tuned to different applications. And it went to all these applications, people at GE who went literally bananas. I mean, they would come running to my office saying, today, I have your device ironing clothes with a steam iron. I'm regulating it. I said, where's the heatsink? No heatsink required. It's inside there doing its. I said, wow. All right. People were building advanced lamps, which are precursors of the CFL. They built heat pump drives. They used it in appliance control. So I'll talk about a little bit of that in this presentation. So these were exciting times. But then suddenly in 1983, yes. 1983, the Semiconductor Products Division announced that there is a new product called the IGBT. And I was surprised because this was an embargo. Suddenly, they've announced this as a product. Came as a total surprise. And I guess the message from Jack Welch somehow didn't get to the marketing people over there. So that's how the cat got out of the bag. And then I was allowed to start talking about it. So, but the first product was, IGBT product was released by GE in 1983, June. After that, the device caught the attention of all the companies in Japan and Europe. And after a couple of years, 1985, they started manufacturing it in high volume. So today you probably buy a lot of devices made by companies from over there. So that's kind of the story. You can read about it in the article in that book. So in this article, I'm going to talk about the IGBT and show you some circuit diagrams. This is the symbol that you must be familiar with. You'll find it in many places. Okay, so what does the IGBT look like in terms of modern devices? This is the actual structure that was successful. So there is a P+ region here to stop the thyristor from acting. But then people had criticized this as having very poor conduction through the PNP transistor. My vision for this was different. I treated this like a p-ion diode with a MOSFET in series, and that worked out to be exactly right. The behavior of the device looks like this, and the green line in the on state. It's more like a diode. And then it's completely gate controlled. And so let's talk about the on-state behavior with this chart. So here if you're familiar with the IV characteristics of devices, this is a typical behavior of a diode. The current goes up exponentially, and then there's some resistance in series here because of the MOSFET, so it starts to roll over. So what I'm showing in this chart is that when we choose the operating point for the device, we have to be cognizant of the power dissipation. Otherwise, the device will heat up too much and become unstable. So the usual value used is about 100 watts per centimeter squared, and you can graph that on this chart. So the intersection point gives us the operating point of this device. And you can see that it is at a value of 100. So 100 turns out to be pretty good for power devices, because then you can make small chips and get good current handling capability. But the other beauty of this device is that you can scale up the voltage. So I have lines for 300 volts, 600 volts, and 1200 volts, and they lie pretty close together, saying that we can scale up the voltage and use it for more and more applications. In contrast, the power MOSFET that I showed you earlier just collapses in terms of performance as you go up in voltage rating. So the IGBT has been found to be an excellent device due to its low on-state voltage drop, medium to fast switching speed, and good blocking voltage scaling. And today there are devices available with ratings of at least up to 4,500 volts and even more. So there are now manufacturers all over the world manufacturing this device, and I think the sales volume exceed about $10 billion. And these are used in every sector of the economy. So I'll go over some of these in my presentation, but due to lack of time, I can't cover everything. So I wrote a book in 2015 to try to document all the applications for the IGBT. To me, this was a bit of a voyage of discovery. I even didn't know it was used in all these places that I was finding as I was searching the literature. So it was a fun book to write. It became much bigger in size than I expected. And to my surprise, it won something called the Pros Award, which I had never even heard of. I didn't know books get awards, but the publisher was very excited. And none of my other books ever won any awards, so this was really cool. And so I've now written a second edition that came out earlier this year, 2023. It adds even more applications into the book because they've grown since 2015. All right, so you can see here, the IGBT is used in a lot of places. So let me show you a few that you encounter every day. So one of the cases is the washing machine. I hope you're washing your clothes. I'm sure you are. So IGBTs are doing the job of running the motor inside the machine. In fact, my machine at home says inverter driven. So I said, that's great. Another place that you'll see it is in flat top cooktop machines. So induction cooktops. So here the IGBT is used to create a high frequency power for the resident induction coil. And then you put your pot on it and you couple the pot to the coil. Another application is in the microwave oven. I thought that was a surprise to me, but I found out that the reason it's used is it allows you to make a high frequency power supply and shrink the transformer. And the weight of the transformer went down by 10 times from 4 kilograms to 400 grams. Imagine the convenience this gives you when you're installing this microwave, or if you have a tabletop one, you can move it around more easily, right? So this is very nice. And there are many more applications that I'm showing you here for the device that you will encounter every day. Okay, let's look at another sector where it's used, which you probably don't know about. It's widely used in the medical sector, including GE. So it's used in X-ray machines for the power supply. And what I found is that using IGBTs, they make the voltage much more precise, which removes a lot of graininess in the X-ray machine. So it's has a direct impact on the image. And then it's used in CT scanners to power the X-ray tube, MRI scanners to drive the gradient coils and other magnets. It's even used in ultrasound machines or neonatal care, where the IGBT drives the transducer. And then it's used in even eye surgery. So these are lots of places which I hope you won't have to use because you're healthy. But another one that I was very impressed by is it's used to create the defibrillator. These would not be possible without the IGBT. And the cool thing about this is it's saving 100,000 lives per year just in the US, and who knows how many more around the world. And these are now very commonly deployed in buildings and airplanes and so on, because you have to reach the victim within 5 minutes to be very fully effective. So this is a challenging application because what you are applying is a shock that's a 2000 volt shock at 100 kilowatts. And it's a biphasic waveform. And only IGBTs can accomplish this in a very compact form factor. And so this is the circuit that was described in the IEEE spectrum, if you're interested. Okay, moving to another sector. This is the transportation sector. For a very long time, the Kittering ignition system was used with a mechanical distributor that's shown here for controlling the spark plugs in your car. Most of you are too young to even remember this. It's all gone electronic. But when I got my first car, this is what was in it. So you had to tune the car regularly because this was not very precise to begin with. And then these arcs would create variability. It would change. And so if you wanted good driving efficiency, you had to tune the car regularly. Well, all that went away with the availability of the IGBT. They could make an electronic ignition system as shown here. Now the IGBT controls the current in the primary, which feeds the secondary and the spark plug, because this, of course, requires a very high voltage. If you read my book, you will find that they are now controlling not just an instant, but the whole waveform fed to the spark plug. And by doing that, they can make sure all the gasoline is fully consumed inside the cylinder, and it improves the efficiency by at least 10%. Billions of these IGBTs have been sold just for this one application, because we drive one heck of a lot of cars, right? So this is a big application. But the other big one in transportation is, of course, hybrid electric and electric vehicles. This is the first hybrid electric vehicle, to my knowledge, from Toyota, the Prius in 1997, that was fully successful. I mean, electric vehicles go way back to the early 1900s, if you read the literature. But these were the first modern ones that were successful, and they then brought this to the US around 2000, I think. This is a picture of the Toyota hybrid Camry that I drive now, because I want IGBTs to bring me to work and to the supermarket wherever I'm going. So these IGBTs do a lot of functions inside your car. They drive the ignition system of your car when you're using gasoline power. They drive the motor through the battery power. They even do regenerative braking. Okay, so that's not the only place you'll find IGBTs. All electric buses, electric trams use these devices. You travel around the world, you'll find yourself being driven by IGBTs. The Boeing Dreamliner now use the IGBTs for the all-electric plane. They've even found a way in cruise ships and LNG carriers to propel those big vehicles as well. But my favorite one is probably also this application, which is high-speed rail. So this is a picture of the three-phase drive to the motor in the rail, and a picture of one of those trains. And I had the privilege of actually riding in the Shinkansen in Japan, the Sapsan in Russia, and even the Shanghai Maglev. So it's fun to do that. Okay, another application, turning to the industrial sector. This is in numerical controls. So the history here is that GE had no viable business in industrial controls. And then with the availability of the IGBTs, I designed not only an N-channel, but a P-channel IGBT, complementary devices. They combined all of this with a lot of smarts and created something they named GE Genius IO product. It is still available, but at that time it was a revolutionary idea. And with that idea, they were able to win the manufacturing plant that GM was installing for producing the Saturn. So it was a big deal for GE. They went from nothing to number 2, I think, in numerical controls. So I found an old paper just to show you this stuff dates back quite a ways, where they're using IGBTs to run motors in robots. And then a lot of other places in the industrial sector where IGBTs are used. It was amusing that somebody wanted me to speak at a steel conference. I said, I don't work on steel. Why are you asking me to speak? Oh, but all our steel mills are driven with IGBTs. I think it'd be fun if you came and talked about it. I did not take up that invitation, but that was an interesting invite. But on this, while searching, I found one thing very interesting in terms of arc welders. It has now become fashionable for the arc welder people to put a sign on the arc welder saying IGBT inside. So I look upon this like you buy a PC today or a laptop, it says Intel inside. Now it's become fashionable to put IGBT inside. It apparently sells better when you do that. All right, turning to the lighting sector, one of the big places where the IGBT has been successful is in creating the CFL lamp, compact fluorescent lamp. This is a very challenging application because all the electronics has to fit in the base of this lamp, so you can screw it into your standard A-line lamp sockets. It heats up over here, and you have to handle the power as well as all the control circuit. And you can only do that with the IGBT. So this is an example of one such control circuit published by Motorola. Today, I think they've sold more than 20 billion CFLs, and they're used around the world. Of course, this is between 1990 and 2020. Now, of course, LEDs are getting more adopted. So the era of the CFL may be ending. Then turning to the renewable energy sector, it's widely used for solar power. In solar power, you're taking DC voltage produced by the solar panel. It could be a solar farm or a rooftop solar panel. And then you cannot deliver that to the home because what you need is well-regulated 60 hertz, 120 volts AC. So that is done by using the IGBT inverter and fed into the home. The same thing is true for wind power. In the case of wind power, you have variable frequency output from the turbine, but you have to convert that into a highly regulated 60 hertz for feeding the grid. So that is also done with IGBTs. Now, one of the interesting things is that with the IGBT, it became possible to eliminate the gear train, and that was a great convenience for the nacelle that hosts the turbine motor at the top. And I found this interesting quote in Electronic Design magazine from 2004, which surprised me. It says, progress within the IGBT technology has made the biggest single contribution to wind turbine advances over the past several decades. So this was not taken trivially by the wind power industry. All right, so let's look at some social impact. And this is something that Dr. Stansel, department head, suggested I look at because of the widespread use of the IGBT. So I spent some time analyzing this and published some papers and then documented this. So I took what has happened with IGBTs from 1990 to 2020 and found that the electronic ignition system has ended up saving us about 1.8 trillion gallons of gasoline from being consumed. By applying adjustable speed motor drives, we've saved 73,000 terawatt hours of electricity. The compact fluorescent lamp has saved us about 60,000 terawatt hours of electricity. When you don't use the gasoline or electricity, you save a lot of money. So consumers have ended up saving money. You may not appreciate it when you're pumping gas, but if your car is more efficient by 10%, you're spending 10% less, right? So all that savings is documented here, and it adds up to a whopping $33.6 trillion. That's not a mistake. Big numbers. In addition, utilities did not have to construct power plants because you didn't have to provide this power. So they have saved building 1,366 1 gigawatt coal-fired power plants, saving us $4 trillion. And as I said, consumers have saved $33.6 trillion as well. But this also has another impact, which is in terms of our carbon dioxide emissions. So if you don't consume gasoline, then every gallon of gasoline produces 19.4 pounds of carbon dioxide. So you offset that. When we produce electricity, we do this a lot with coal-fired plants and natural gas that also produces carbon dioxide. So you get about 1.3 pounds of carbon dioxide for every kilowatt hour. So you add all that up, and it comes to a very big number, as you can see. 181 trillion pounds have been saved because of all these energy savings. To put this in context, if you look at the global footprint for people, the emissions are about 8,000 pounds per person, per capita emission. And we have about 7 billion people. So we're talking about global activity producing 56 trillion pounds. So this one technology has helped reduce our impact by about a 3-year time span, of course, over a 30-year time frame. But I don't know of too many technologies that have had quite this level of impact. Okay, so because of this, it was interesting that one of the people, a reporter, wrote an article in Forbes when I was inducted into the Inventors Hall of Fame. And he said, Jay Baliga is the man with the world's largest negative carbon footprint. I said, oh, that's cool. I like that. But then the Inventors Hall of Fame said, we have to capitalize on this. So they made me into a superhero. Not too many people get to become superheroes. That's pretty cool. So when they did this and sent me this artwork, I said, well, what is going on here? I said, you have strapped on IGBTs and you're taking pollution and converting it into electricity, clean energy. So, oh, I like that. That's really good. Well, my costume is at the dry cleaners, so I didn't bring it anyway. Okay, so now I want to give you a little bit of history of what happened after I left GE and came to NC State, because I have to cover actually the 35 years I was here. I have not even reached that point yet, right? I'm just starting my career at NC State. So the first thing I did at NC State is to propose and create a consortium. It's an international consortium. This is the first international consortium I found at NC State. All the other ones were either NC North Carolina oriented or maybe national. And I managed to get about money from all over the world, about 700K per year, and served as the founding director for 10 years. One of the unique things about this, we of course produced lots of reports and patent disclosures, et cetera, but I'll tell you the unique stuff. So one of the things I did is created a new model for filing patents and licensing the technology at NC State, because I was surprised that when I talked to other center directors, this was never emphasized. They did not worry about this, but I was developing a lot of intellectual property. So to my surprise, they then started sending lots of other center directors, including people from UNC Chapel Hill, to me to say, we want to see your model and see how we can adopt it. So it became quite an important development. So because of this model, I was able to generate 50 US patents in 10 years out of this work. That's pretty good. I don't think too many other faculty were producing that many patents. All right, so these are the list of sponsors. I appreciate their support over the years. In addition to these corporate sponsors, we had money coming in from government agencies as well, DOE, DOD, and EPRI. And using this, we were able to show these MOS gated thyristors, some work on smart power ICs that I mentioned before, and most importantly, these two categories. So this is the silicon carbide-based power devices, and these new devices based on a new concept called charge coupling. So in this talk, I'm going to cover next this device, the silicon split gate MOSFET, as my second ideal switch. And then after that, I'll talk about the silicon carbide MOSFET. All right, but before that, it was mentioned that I had 4 successful startup companies. So you might be curious what I did there. So even if you're not, I'm going to tell you. So first was Micro Ohm Corporation. This is the one where we commercialized the TMBS rectifier, and it went eventually to Vishay Siliconics, and they claim this is the most successful rectifier they have made in the last 25 years. So it's pretty good. Then I commercialized the super linear silicon RF power MOSFET. This company received a $10 million investment from Fairchild, and we created this product for cellular base stations. CEI declared as the spin-off of the year, which NC State liked very much, and it was eventually acquired by Fairchild. Silicon Semiconductor was the next company where we created a new kind of planar MOSFET that I patented. And this was used to create what are called sync FETs and control FETs, which are in the voltage regulator module, which are all inside your PCs and laptops. This was licensed to Linear Technologies by the company, and it's still being manufactured in pretty good quantity. I heard the sales may have exceeded 150 million now. And then we had another company, Jayant Semiconductor, where we tried to commercialize the split gate GD MOSFET. This is based on the 2D charge coupling concept. This was successfully licensed to Alpha and Omega, and here's a picture of their product. But after that, lots of companies started copying this, and it's now become the dominant technology for power MOSFETs. All right, so that's number 2. So I'll talk about that now. So what is this charge coupled concept, and how does it work? I will not tell you because it's too complicated. You have to read my book or take my class next semester. But this is the basic structure, which contains a gate to control the MOSFET. And then it has a source connected electrode in a deeper trench with a thick oxide. So this produces what's called 2D charge coupling. It's listed here. And the bottom line is what I'll tell you. It improves the on resistance, which is what we are trying to achieve in making ideal devices. So you can see here a shift from the blue line for 1D physics to this red line with 2D physics. It's like an order of magnitude. And you may think that, oh, but it's not doing a good job here. But if you look at what the current products are in 1D, they deviate a lot from the ideal. But what Alpha and Omega produced with this technology comes very close to the red line. And so we have actually an order of magnitude improvement across the whole gamut of voltages. So these are used in computer power supplies, automotive electronics, places like that. Okay, then there was a period from 2008 to 2018 where we worked hard to bring a NSF ERC to NC State. So this is after I finished doing my companies. And this was a huge endeavor, involved 4 universities. And then we had to make a big proposal, very tough to get funded, but we were successful. And it ran successfully for 10 years. It's still there at NC State. So I served as the device thrust leader, which is a role down here. And we created lots of innovative devices for use in solid state transformers and fault interruption devices. This is a list of some of the devices we created. Okay, so next I want to move on to another ideal switch created out of the wide bandgap semiconductors. I mentioned silicon carbide. So this idea is aimed at reducing the resistance of the drift region in what I refer to as unipolar devices. This is Schottky diodes and MOSFETs. So this, in silicon, this drift region resistance becomes very large and limits performance. So I looked at this at GE in 1979 and asked myself, if I replace silicon with another material, can I improve the performance, and what should be the properties of that material? What's interesting is at that time, everybody seemed to be very happy making silicon devices, and no one had bothered to ask that question. So if you're the first one to ask a question and you can produce an outcome, it becomes very impactful. So I published a paper eventually after GE allowed me to release it. They didn't want to talk about it for a while, in 1982. And it showed that the resistance here, specific meaning per unit area, is related to the breakdown voltage, which dictates the thickness and doping here, and these basic properties of the material. This is the dielectric constant, the mobility, and the band gap cube. So because of this equation, you can see that we can reduce resistance greatly by increasing the band gap, right? It's in the denominator. So that's why wide band gap, bigger band gaps are now very popular in terms of making power devices. But the correct equation for the resistance actually is not band gap, but has an electric field, EC, which is called critical electric field. But that was not known for materials in 1979. And a lot of work that was done subsequently to measure this, including in my lab. So this denominator here is now commonly called Baliga's figure of merit, BFOM. And it is this denominator as pointed out here. And you can also see that it's equal, if you reverse this equation, to 4 BV squared divided by R on specific. So people make devices out of different materials. They measure the breakdown voltage, they measure the resistance, do this calculation and see how well they're approaching the ideal. It's a very powerful equation. So that's become very popular. It's become so popular that I thought I'd show you some recent publications. And these publications have my name and figure of merit in the title of the paper. How weird is that? Okay. So now I'm asking you a question. If my name appears next to the authors in the title, can I count these as my publication? How many of you will have this problem? I think I'm one of the few people who has this problem. So far, I'm not counting it this. All right, so let's move on to how this works. So we'll look at a power MOSFET and look at its drift region resistance, and you can compute it by using the thickness, doping, and mobility. You have to know how to relate that to the basic properties of silicon carbide, and these are derived in my book. So if you use these numbers, then you get this line for silicon carbide. This is the line for silicon. Now, this is the resistance per unit area plotted against breakdown voltage. So low resistance is good. And look what we have done. With this approach, we have reduced resistance by 1,000 times. This is enormous. If you have a technology that improves things by 2 or 3 times, there's a lot of excitement. People start investing in it. We're talking about 1,000 times. You can imagine the excitement. Okay. So that's why we had investments in silicon carbide for the last, I would say 20, 30 years in order to get us material to bring this to fruition. But it was not easy to do this. There were some major roadblocks. One of them is called read-through breakdown. Others, gate oxide failure, low inversion channel mobility, high threshold voltage. So all of these challenges had to be overcome to make the practical devices that you're seeing in the market today. So one way to do this was an invention of mine called the AccuFET. And it also has the shielding concept. The combination of these two solves all of these problems. This chart shows how the accumulation channel mobility, threshold voltage is reduced significantly, allowing us to drive these devices more easily. So this is a landmark paper that we published in '97 demonstrating this. And I have one student here who worked with me also on this at one time in my lab. He's now, of course, well graduated and doing greater things. All right, so here's a chart I pulled up from a paper published by Dr. Palmer from Cree. Unfortunately, he passed away recently, but he is one of the founders and a big proponent and champion of this technology, as well as technical contributor. So he showed this chart with the black dots at a conference called IEDM, and I added a couple of red points for devices at lower voltages. And you can see that for higher voltages, we have actually approached the ideal performance. So we're doing really well. On the other hand, at lower voltages, we are much better than silicon, but we can improve them even further. So that's mentioned here. Now we already have many products. So where are these products going to be used? This is a plot of device current rating versus blocking voltage, showing where various types of technologies are used, power MOSFETs, IGBTs, thyristors, and where we will find these devices will be in this domain. It greatly overlaps what we are doing with IGBTs. But IGBTs are far cheaper and in much greater volume production, not easy to displace. So this is a challenge for silicon carbide. To address this challenge, you have to show some system level benefits, that there's an overall improvement at the system level, even if the chip costs more. So that is how the industry is approaching this. They're also increasing circuit operating frequency to make things more compact, reduce the cost of passive elements, and show increased efficiency. So one of the ways to promote this was to create a manufacturing institute, which was announced by President Obama, and I and others at NC State put together a compelling proposal together with industry, and we were successful in winning it against a lot of stiff competition. It's a $40 million project that is already finished. It ran from 2015 to about 2020. And it had one-to-one matching funds from the industry. So these are the early people in industry who joined this consortium and universities as well. And this was so-called ecosystem. So the goal again was to drive down the cost with all these improvements. So what was my role in this? I actually created a technology called PRECISE, called Process Engineered for Manufacturing Silicon Carbide Electronic Devices. I think that's a cool name because it has SIC in it. So these are the devices which can be made with this technology. These are made in a foundry by us over many years, and they are well documented. For example, this chart shows the distribution of parameters for one of the devices, the JBS-FET, showing very tight distributions that allow us to make these devices. So companies have licensed this and are using it. But I also wanted to improve the high frequency operation performance of these MOSFETs. The industry was focusing only on the RDS-on as a primary driver for what they were doing. I felt that if you're going to open up the market with higher frequency of operation, we need to optimize for that as well. So this is one of my inventions called the BG MOSFET. This is also mentioned in that invention, SG MOSFET, and we successfully built these devices. Ki Jeong Han, who worked with me, is here today, so thank you for showing up. He now works elsewhere after graduation. All right, so here's the measured performance, and you can see here in red how much it improved the performance. So to put this in context, Power America made a roadmap saying we can improve this figure of merit, which is a product of R and Q, which is the overall high frequency behavior. We'll try to improve it by 10% every year for the next many years. Well, we achieved 400% by doing this device. So it's pretty nice to make that advance. Another idea was to change the cell topology from a linear cell to this octagonal cell. And again, Ki Jeong worked on this with me, and we were able to show significantly better performance with this device structure. All right, so where's all this going? It's going into electric vehicles in a big way. Today, IGBTs are dominant, but by using silicon carbide, companies like Toyota want to place these devices inside the main drive for the engine. They call it the PCU. So by doing this, they have a pictorial diagram showing how much things will shrink. If you look at the picture, it's actually the same picture with a smaller size. So it's not really implemented, just showing schematically what can happen. All right, so that's the proposed expectation, and you can get about a 68% reduction in power losses as well. So a lot of manufacturers are now considering using silicon carbide. Today, almost all worldwide manufacturers are committed to building electric vehicles. That was not the case some time ago. But now everybody is on the bandwagon, and IGBTs have been used since the 90s, and silicon carbide devices are being adopted since about 2015. So last but not least, let me talk about the ideal device number 4. So this is, according to Professor Bhattacharya, the true holy grail for power electronics. He's been wanting this forever. He says, why can't anybody make this for me? I can't build what I want without this. So finally, in about 2020, a little before that, I invented a device that makes this possible. So what's different is that it's a 2-quadrant device, so it works in the first and third quadrant and has to have perfect behavior in both quadrants: symmetrical blocking, symmetrical current conduction, control, etc. Okay, so to give you an idea of what people were doing, they were trying to build matrix converters, and they were using large numbers of components to kludge this together. So sometimes it would be 5, sometimes it would be a little less, but they all had high on voltage, which is bad for losses, and some of them had very high switching losses. So I've now come up with this device. It's at the bottom, which is a simple monolithic 4-terminal device that does all these functions. So according to Bhattacharya, this is a major innovation. How is this done? It's actually done in a very simple fashion. The idea is clever, but once you do it, people say, oh, that's very obvious. I mean, of course it's obvious. Once somebody has shown you how it works. So this contains 2 JBS-FETs that work in tandem, and we had already been building these, so we build these side by side, and the current flows from one through the substrate to the other. So it flows vertically in both devices, and I won't go into the details, but this is very efficient. and it makes a perfectly symmetric device, which other people were not able to do. So fortunately, DOE gave us good funding to demonstrate this. And we've been successful in building one of the largest chips at X-FAB, the foundry. This is a 1 centimeter by 1 centimeter chip. And with this chip, we had also, this was also designed by Ki Jeong and one of my other students more recently. So this chip was packaged in an excellent way by Professor Hopkins and his student. And you can see here, it is put in a package with a huge number of wire bonds to bring the wire bond resistance down. Otherwise, it will completely defeat the resistance of the device. And then you end up in a module that's encapsulated here with just 4 terminals. So there's the circuit symbol we have for it, and it shows it blocks 1.4 kV in both quadrants. In terms of the on-state, the first quadrant, you can look at this one. It has a on-state behavior with a resistance of only 50 milliohms. On the third quadrant, again, it has exactly symmetrical behavior with 50 milliohms. So that's what people want for these applications. So using this device after many years of work, I'm going through 3 years of work in like 1 minute. So after many years of work, after we packaged those devices, they were able to put it in an inverter. This is done, of course, by Dr. Bhattacharya and his students and a postdoc. So they were able to build a 2.3 kilowatt, one single phase inverter with some very good performance numbers. So that brings me to my conclusions. So what I've tried to do in this presentation is to focus only on a few things that I have done as innovations. And the 4 things are listed here. You saw that the IGBT has become ubiquitous in terms of its use in society and has had an enormous impact on energy, cost, and carbon dioxide savings. The GD MOSFETs are now used for all lower power levels in computers, servers, and data centers. Silicon carbide MOSFETs are now going to reduce size, weight, and improve efficiency, which will accelerate the adoption of electric vehicles and renewable energy sources. And then these BiDFETs enable matrix converters. And according to Dr. Bhattacharya, this is the next generation of power converters we can expect. So I've been blessed or fortunate to be recognized with a lot of awards and honors over the years for the work I've done. So I'm grateful for that. And then I'll end by acknowledging the support I've received over the years. So first, of course, by the General Electric Company, including the chairman, and then all my NCSU sponsors, more than 20 companies, approximately 20 companies that supported PSRC, the National Science Foundation support for freedom, DOE support for Power America, and of course, the recent support from DOE-SETO. And then, of course, I want to thank my 40 plus graduate students who made my life interesting and productive. So thank you all for doing that. And with that, I'll end my talk.
Very much, Baliga. So we'll move into a Q&A, and we're happy to take questions from the room, and I'll try to also bring up Zoom so we can see if there's any questions there. But does anyone in the room have any questions? I'm happy to kick us off.
Oh, sure.
I have a light one. So there's a lot of students here in the room, right? And
Sure.
and I'm sure they were watching your presentation and admiring all the achievements and probably wondering to themselves, how do I set myself up to be able to do something similar? Right, they're at the beginning of their degrees, they're doing their research, looking for opportunities. So I was curious if you could maybe comment a little bit on any suggestions or advice you have for someone to think about how they can make impact, right? How do you look for that opportunity or identify a problem or think about a novel solution that could be patentable or result in something that might be interesting to industry?
So let me start off by saying that you don't want to do any work to get an honor or an award. That's never been something that I try to aim for. It happens. If you do good work, you'll automatically get honored. So don't worry about honors and awards. Focus on doing high quality work. But the other part is be innovative and believe in your idea, like the IGBT. If I didn't believe in my idea, I would not have had the courage to pitch it even before I made it to the chairman and survive. I would have been scared to do that. But you have to believe in your idea and then be willing to do the groundwork to be sure it works, that it's right. And once you have that confidence, you can sell it to people and hopefully be successful. But it's not easy. It takes a lot of things to come together, like I was talking. And if you're fortunate, those things will come together. Sometimes you have to make it happen by starting your own company, for instance. So you may want to do that too. That's now very not too hard to do at NC State. There's a lot of support to do that. So I would suggest be innovative, but believe in your ideas and try to make them happen. Yes.
Thank you. Any other questions? Yes.
Can you describe a time when you took a risk and it didn't pay off?
It's the opposite end of that last one.
Yes. So I have 123 patents. So these, obviously, many of those other ideas did not pan out or weren't worth pursuing. And other ideas that I thought were great did not, the industry didn't think it's worth taking them into production. So that happens all the time. It's not unusual. Actually, it's unusual to have an idea that goes all the way and becomes very impactful. Yeah. So I never dreamt, for example, that the IGBT will be this impactful. It's just quite amazing to me. So I feel very fortunate that I had a hand in doing that and making it happen.
Oh, there's a question that's just pop in here and open this up. So, this is from Dr. Bhattacharya.
Uh-oh.
So do you want to read it out or I can read it out?
Can you please tell students and all how the devices impact power conversion systems? So understanding of devices for PE students is critical. That's good. Okay. So as far as how they impact power conversion systems, go take Professor Bhattacharya's class. That's my advice. So seriously, okay. So, but I think what's important is that those of you who use devices can gain a lot from taking my class, for example, because then you understand why the devices have limitations. Otherwise, you take it from the data sheet, you use it, and you don't know why it's not doing the perfect thing that you want in the circuit. And the other thing you don't have a perspective on is why isn't that ideal switch available? So I gave you that story today. Okay, it's not easy to make it ideal. There are lots of things that come in the way. So I would say, yeah, and I tell my students who are doing devices, take the power electronics class so you understand why you're designing something and what is it that is needed by the people. So if you develop something new, it's very helpful if you know what people want, because it is not very practical to create something new and throw it over the fence and say, okay, I hope you'll use it. Doesn't work like that. Other people won't show any interest in it. You have to show that it has some value. Okay, so you have to have knowledge both on devices and in power conversion systems. So that's the best answer I can give. You want? Is that the only question online?
So far, yes.
Yeah,
the
okay.
only one I see
Okay.
online.
That's fine.
Yeah, I'll just hit that one there so we archive it. Oh, and Subhash
Oh.
says thanks. Any other questions here in the room?
Yes.
Mr. Baliga, there's different wealth of information through your startup experience. I'm thinking the students might benefit from there's so much that goes into
Oh, yeah.
technology.
Yeah.
From
Yeah.
inception all the way to commercialization, right?
True.
Maybe share your experiences with us with these different startups and the whole process of commercialization.
Okay, so this question was asked by Ravi Chilukuru. He actually worked with me on one of my startups, so that was another phase in his life after he was a graduate student with me. But if you want to take something from idea, you first have to do the research to prove it works. Otherwise, nobody will accept it. At GE, the circumstances were unusual, as I told you. I had to take the risk and not even made it and convince people. But that's not generally true. You have to first make it, prove that it works, and that's common practice at the university. And then after it works, you have a feeling for where it's going to be used. So now the next question is, how do you commercialize it? So I've tried various models to your question. So the first model I tried was with micro-ohm. I said, I don't want to stop doing what I'm doing at the university. I love what I'm doing. I'm teaching students, doing research. So I'll start this company. And this is because venture capitalists came to me and said, would you like to start a company? We have money and you have the most patents over here. So we thought you should start a company. I said, okay. So I said, I will do it, but I want to do this as a licensing model where I help the company to create the product and I'll help them in terms of the design and get this product made. And so that was successful. As you saw, Vishay Siliconics did it, and it became the most successful rectifier in the last 25 years for them. But then the VC said, well, that's just giving us some licensing revenue. We really want to create a company with employees and take it IPO and all that stuff that everybody dreams of. Says, you have another idea. So then I thought, how can I have a compelling idea that I can compete with a startup? Okay, it's very tough to compete with big companies in the same space they are making products. They have all that infrastructure. They have all the applications people. They have all the pre-existing customers. You can make something better, but why would somebody buy it from a small startup with all the risk put in their systems, right? So I said, I need to find a product space where the devices have a lot more value than power devices, conventional power. So power devices sell for very low cost, under $1 a piece most often. That's a very tough business. Your margins are small. So I said, where else is it used? So I found in the RF base station space, Motorola is a dominant player with 80% of the market. They're selling LD MOSFETs. They're charging $200 a piece. I said, that's better than $1 a piece. And can I make something that is better than what Motorola is doing? So that's, again, not easy to do, of course. They have honed this for years and years. But then I found that there was distortion in their transistor. And because of that, their customers were taking the transistor and buying them for $1,000. And they were spending $2,000 to get rid of the distortion. I said, oh, this is terrible. Paying just for the transistor, then you're paying something to fix the output. And then the whole efficiency goes down. So I said, can I change the physics? And again, as I said, I discovered this new physics called superlinear, which I thought would be already have been discovered. I mean, people have been working on MOSFETs for ages. I couldn't find it anywhere, and they issued patents to me. So that was the discovery that then said, okay, so this could become a unique high-value product, right? And so now I had to say, how do I get money to do this? So the VC said, sure, we'll give you money to start the company. But I said, that's not enough. I need a place to build this. Where am I going to go and build this? I don't want to go to Taiwan or some long, faraway place. I need some domestic partner. So I knew Fairchild very well, and I knew they did not have a product in the RF space. So I said, okay, maybe I can take these factors and convince them that this is a good investment. And with one PowerPoint presentation, I got $10 million. Okay, that's pretty good. And then more than that, they gave me access to their production facility with another 10 engineers. And we built this device within 6 months. This is amazing because they had they said, this is a new thing for us. So we're going to bring in all these consultants. And the consultants were saying, nobody's ever done anything like this. 6 months, we had a working device. So you have to prove yourself as well. But you have to have a lot of things coming out right to make it work. Of course, you can do a traditional startup. You can try to compete with people, but that's actually harder. Yeah.
Well, thank you very much
Okay.
for the presentation and for answering all these questions. So before everyone heads out, I also wanted to remind you, as